Wonderful. Hi. So I'm not as ambitious as the best of all worlds. It's going to be just the best of both worlds. Talking about high performance recommendations using NIFs, which are C functions embedded in Erlang. Also, throughout this talk, I'm going to use Erlang and Elixir interchangeably. To me, they mostly mean the same thing. Really, this talk is about how I just can't stop writing C code. Even at an Elixir conference, I'm going to talk about C. So yeah, that's me. I'm Shanti Chellaram. I work at TPT, and that's my GitHub, where I will upload the resources and code for this this presentation as soon as I have clearance to. And I really like C. Anyways, so I want to talk about our data pipeline at TPT, the problem that we're trying to solve when it comes to building a recommendation system. This is kind of how our systems look right now. We have a website that our customers use. That DB cylinder represents all of our backend databases, which we have like Memcache and Redis and MySQL. And data pipe is our data pipe is our processing, like machine learning algorithms, like bulk processing system, written mostly in Python. And our real-time server is our backend API in Elixir, and that takes in some of the data processed by the pipeline and feeds it back to the website to influence customers and keep that cycle going. So we're going to start in the data pipe and talk about what a recommendation is. Really, we want to just assign some kind of arbitrary numerical value to how likely a user is to like an item. There's a lot of sauce that goes into this that is really not important to this talk, but you kind of get this, this feeds into the next part, which is a matrix of all of our users and all of our items, where every entry is that score for that user. This is huge. We have 25 trillion entries because we have 5 million users and 5 million items. And that's just not feasible for us to maintain in memory in a real-time system. It does work through our bulk processing system, but the turnaround times on that are hours. So we use this thing called feature decomposition. I'm not a machine learning person, so I'm going to maybe fudge some of these terms. But the basic idea is you can factor a matrix into two smaller matrices. And so this matrix of all users and all items turns into two matrices of users by features and items by features that we then can multiply together to get the value for a single entry in the original matrix. And that reduces our space requirements really significantly. We're down to 320 million. And that's something that we're plenty happy to store in memory. That 32 is because we factor it into 32 features. And so we have, that's a little smiley face. So we have three main problems when approaching, that we have to solve to serve this data in real time. First one is that the data is too big, which is pretty obvious here. The second that we'll come to is that the data is too slow. It just takes too long for us to process all of this. And the last problem, which is really a personal problem, is that it's too in Erlang. and I'll elaborate on that. It's not as negative as it sounds, I promise. And so yeah, going back to the system diagram, we're going to zoom in on the real-time server. The interesting part, the part that I actually work on. So just back of the handbook, I went through and calculated how much space this should consume. Each ID is an integer. Each number is a double, 8 bytes. And if we pack all of that stuff into an array, we get 264 bytes per record times the number of records. And if we do the same for Erlang, it's actually well documented in the Erlang manual how much each data type consumes. Floats take 24 bytes, and representing them in lists adds a bunch more overhead as well. And we end up with almost a 4 times inflation on our data. And even though 1 kilobyte isn't that bad, if you multiply by 5 million, you end up with 6 gigs of data almost. And when we were doing this data load in practice, we found, that we hit that 6.2 million there. It's just a little bit more than we expected, or that we desired. So this is our problem. I love these vintage memes. Anyways, so we have too much in memory. And we're going to take this problem and put it aside for a second and go over kind of what the real-time server does, or is supposed to do. So we have this query method. And the basic idea is we take our item data, we map it to get the score of each item in that data. We sort it all, and then we return the top k items. And we're using k because users don't care about what the 4 millionth item in their ranked rating of all items is. They probably just want 100 or so that show up in their search results. And get score is really simple and straightforward. It's basically an implementation of a dot product. And yeah, it's a very straightforward problem. And here's our input parameters. 5 million users, 5 million items that we're calling n, 32 features, which is going to stay constant throughout this presentation, and 100 items for k. And sometimes we want to play with that number because we're doing some filtering on top of this that reduces the total output number of items. But for now, 100 is our base assumption. Yeah, so just going through the code, it's pretty clear that this code is going to take NF plus nlog n plus k for each of the steps to run. And when we measure that runtime, we get this. We have 1.73 milliseconds to return the results for 1,000 items, but at n is 5 million, we get 30 seconds. And that's just not acceptable for a web page. So we're too slow too. And now that we've, I had to introduce that first, the basic algorithm so we can talk about how we're going to start optimizing it. So going back to the space problem, we're going to use something I'm calling, binary packing. So we'll have way less overhead because we're going to just represent all of the data fed into Erlang as binaries instead of in the native Erlang representation. So there's going to be much less space overhead. However, we're not using enums anymore, so we can't use iteration. And there's an overhead in Erlang when we do the actual math to convert from the representation in the binary to the Erlang term. So that's a cost and performance. Here's our syntax. It's actually really easy to write this. This conversion feature, this conversion code, Erlang's got a really nice syntax, or Elixir's got a really nice syntax for writing, representing data in binaries. And it's not the fastest thing, but we can run this out of band. It actually runs as part of our data load step. And here's our iteration function. I'm just calling it bin reduce because it's like reduce except on a binary. And we define a block size because terms inside the binary can be of any size. And we just chunk it up by the pattern match and pass it in to the fun, which aggregates the results into the accumulator. And now our query looks like this. We have our item data and our user row as binary data instead of lists of data. And we can map to the get score, still sort, still take the top k. And our get score method also looks a little different now because we're iterating through binaries. But the pattern matching works basically the same way. And here's our results. As you can see, our space reduction has gone down by a factor of 4. So that's nice. That's what we're going for. But we still have this huge size of a list. And that's because at the end of it, we're still aggregating a giant list of the end results before we sort it and then return the top k. So I created this thing that I'm calling a window. It's just a heap with a bounded maximum size. Here's just the interface for it. You can create a new one defining the maximum size, and you can insert elements into it. And once it reaches that maximum size, it's going to start dropping the lowest element. And so you'll run like a window of size 100 over a list of 5 million, and it'll just keep the top 100 things and drop off each element as you iterate through. So naturally, we want to back this with a priority queue or a heap implementation. I've written this one in Erlang. It's not very, it doesn't have a very fleshed out interface, but it does work. The data structure is called a data structural bootstrapped skew binary min heap, but it's really just a binomial heap, which means we get efficient merging in addition to efficient inserts and peaks. And our delete min is also log time instead of anything worse. So here's just going through the implementation real quick. We define our window with the heap and the maximum size. Our insert just checks to see if we've exceeded the maximum size. If so, we'll just drop an element out. Otherwise, we don't. And converting to list is really straightforward. So now, instead of sorting our elements, we basically have them sorted for us as we go through the list, as we go through the reduction in turn. And we have ended up with this performance characteristic because we're no longer sorting an entire list. It just takes log k. It takes the, proportional to the size of the window to insert and remove items from it. And so we've improved the runtime just a little bit algorithmically. And we no longer consume so much space because we are not generating that huge list anymore. So we're really happy with the end results here. We've got what I'd consider a reasonable memory consumption for our worker, our real-time server. And we save space. So now that we've shrunk the problem size, we're no longer too big. We're still too slow into Erlang. And we've got a good pace going, so I'm going to skip over that mini break. And the changes so far is we've done the packing, we've done the windows. We're as optimized as we need to be in terms of space. Let's start attacking time. With these changes, we've actually slowed down the simple cases of the problems because of the setup time. But we're seeing the win of the algorithmic speed up. And down to 22 seconds is pretty good, but we're not where we need to be. And when we're talking about these like good response times, there's these two numbers that I found quoted on some Stack Overflow post from a book called Usability Engineering in 1993, where 1 second response time on a page makes it feel like it's actually responding to your input, and 100 milliseconds makes it feel like it's instantaneous. We ourselves, generally at TPT, are like kind of aiming for 250 milliseconds for response time. And so we're aiming for 100% or 100 times speed up. It's a little ambitious, but I think we can make it. So yeah, the most obvious, I think, approach to optimize next is by parallelizing the code. I mean, this is Erlang. It's what it's about. And right now, our code kind of looks like this. We create the window, we insert it to it, and then we convert it to a list. But we're going to move to a model where we parallelize and partition out the data, do the same code that we were doing before, and then merge it, and then convert it to a list. And we're going to add an additional input parameter now called p. That will be, wow, that's hard to see, called p, which is the number of parallel workers that we have. And this is really constrained to the number of physical processors you have available or Erlang schedulers you have available on your machine. In practice, it doesn't really help if you try to allocate it like 100 processes and your machine only has 2 cores. So this is a very scary looking partition method. It just goes through and it does a bunch of math to evenly split up your large chunk into p sub-chunks of your item data. And this is actually really efficient in Erlang. There's this notion of a refc binary, a reference binary. So When it comes to binaries larger than 64 bytes, instead of actually copying the binary around when you're creating partitions, it'll just give you pointers into it, and it'll treat that as the data that you're passing around. And our worker method now looks like this. We've just removed the toList at the end of it. And we've added this merge method, which uses the priority queue merge and just adds the sizes of the windows together. This toList method isn't really that important. It's actually called getTop because we remove the elements that we don't care about from the window and then give you the top K. And now our query looks like this, and it's a lot nicer looking. We have our partition, our worker tasks that just go and do the thing, merge our windows together, and do a toList. And so again, like this is kind of what the flow of it looks like. And let's look at the runtime. So just like sketching out what the runtime looks like, we've got like the old algorithm was that NF plus N log K plus K. And now we've had these partition steps. But the partition steps are pretty cheap. They're just cost P. And we've basically subdivided the work part by P because we've reduced N so significantly. And then we've added the additional cost of merging, which is KP log KP at the end. And this is pretty good. We get this really nice speed up when it comes to like massively parallel processing. We're down to 3 seconds on a 16-core machine, which is what our raw AWS nodes are. And it's like a little bit of stretching. There's technically one smaller optimization we can do, but this is about as fast as possible as you can get in Erlang. There's not a whole lot more you can do within the bounds of the system. We kind of like try different, like maybe more efficient heaps or things like that, but we're kind of like hitting a wall here. We were hitting a wall. So because we're as fast as possible, I'm going to go ahead and cross off too slow and just take us to Erlang of a situation. So we are going to go into the NIFs now. NIFs are C code embedded in your Erlang process, and that makes them very risky. It's difficult to write safe NIFs. It's difficult to reason about the safety of your Erlang system because a bug in a NIF or a memory leak in your NIF, Erlang can't really do anything about it. It's going to, and like it just threatens to crash your Erlang system in a way that isn't well defined. And there's this lovely illustration of what can happen when you use NIFs. But yeah, so we want to be very judicious about where we use NIFs, and like knowing that we have this cognitive overhead of our failure modes. We want to keep our NIFs really, really small, and we want to keep them very targeted to where they're going to have the maximum impact. And to figure out where we're going to do that, we used an Erlang utility called fprof. There's a whole family of tools, cprof, eprof, and fprof. These are the built-in Erlang profiler utilities. And they're really straightforward to instrument your code. And they give you a result in your IEX prompt that looks kind of like this. You get a little report printout of where time is being spent in your code. And with this, I guess it's a little hard to see maybe, but the 95% of the program time is being spent in the record sum, which is the dot product function. So it's pretty clear here where we want to target our speedups. So we're going to create a home for our NIF. This is just kind of what the boilerplate loading NIF code dynamically function does. We load our, we have this like stub method at the bottom here that gets called if the NIF was not successfully loaded. And our NIF code is the C that we'll see here. This is basically it. It's a really straightforward, simple problem. This is what it looks like if you're writing it just in C, but because it's NIFs and it has to interact with Erlang, you end up with this mess. This is all the boilerplate that goes around correctly parsing out the data that you get in and performing the check that you need to do. It's not really that bad, I swear. Anyways, oh, and we ran into this issue. I was really confused as to why our IDs were coming back completely wrong, and we were getting items that didn't exist, and the ordering of elements was completely off. It's because we need to specify endianness. Erlang by default uses all big endian, and it depends on your computer whether or not it's in big endian or little endian. So there's a conversion step there. So that was something that tripped me up that hopefully you won't. And at the end of it, we ended up with a performance slide that I did not get. But it's okay. There'll be another performance slide at the end once we talk about the next optimization, which is NIF windows. I didn't go through. It took a long time to kind of reverse engineer the process through which I got to the end state. But the next place for optimization based off of fprof results was the windowing code, which makes sense. It's the stuff in the tight loop, basically. And here we're going to have a larger NIF modules. It's going to have 5 or so functions in the interface. So we're going to define our Erlang interface first, then create a C implementation, a pure C implementation, because you saw how the boilerplate Erlang code can get really hairy, make it hard to understand what's going on in the function. And then we're going to create NIF wrappers around that. And I'm going to just hand wave through a lot of this. Here's our window code. It's the same thing. And we're defining these struct types. Our window there at the code there at the bottom is pretty straightforward. For the reads, I'm not even implementing read as a function. We're just going to access the struct fields directly. And here's our NIF declaration code. I don't really think there's a huge point into getting into how we do this, like the details of the window code and the NIF. Suffice to say, we used a binary heap instead of a binomial heap, and just because it was easier to write in C. And we got to this point where we want to take advantage of C and write to mutable state over and over again. We don't want to copy the binary heap over and over. And everything that we pass into the beam has to be immutable. So we work around that by defining a handle type. And the beam manages the handle and passes that around as an Erlang term, but it contains a pointer to some mutable state that we've allocated separately outside of the Erlang VM and are going to manage ourselves. And Erlang is actually completely fine with this. It's totally happy with this. And in recent versions of Erlang, they've added this notion of resource types, which are kind of first-class citizens in the Erlang type system and do some checking to see if the data that you got back from your NIF is the same as the data that you're passing into your NIF. And it lets you register a destructor so that when the Erlang VM thinks nothing is going to be using your Erlang term anymore, it's safe to delete the C memory associated with it. And this is what it looks like. It's a huge function call at the bottom, but the destructor is just free this code. And that's what it looks like in Erlang. In Elixir, we just get this reference type that contains some opaque blob. And now our worker has this impl. This is taken straight from our production code. We just have a NIF impl module, a NIF window module, and iterate using those. And we've got the speed up we wanted. We still have like a slightly slower than native, like at the very small end, but the scaling is just huge improvements throughout. We're at 300 milliseconds for our 5 million data set. That's split into 16 processes at the Erlang level and then processed by C for the most part within the worker. Yeah, there we go. That worked. Yeah, so we're cruising. And we're at the top of our proverbial mountain now. We've done it. we hit the 100 times speed up, and this is kind of the overarching assumption going into this was that we don't have sharding, we don't have coordination across our multiple nodes to separate out the work. And those systems are complicated to build out and complicated to reason about. It's a solved problem, but there's a lot of operational work that goes into it. And we're still a little short of 250 milliseconds. And there's the next step that we could take of basically taking the entire worker code, the NIF dot product and the heap and the window, and combining it all into one big block of C code and calling it to that instead of returning back to the Erlang VM every iteration. But that's for a later talk because we haven't gotten around to doing that. It's going to be a lot of additional overhead. Whenever you have there's a talk by Andrew Bennett that I'd highly recommend watching. Whenever you've got a NIF that takes longer than about a millisecond to run, you get some serious blocking issues with the Erlang VM, the Erlang scheduler. So we haven't dove into that yet. But that's next step. So those are our three problems solved. We have injected a suitable amount of C into this. And I kind of breezed through and glossed over some things, so I'd be happy to take any questions. And that's the end of this talk. Any questions? I actually can't see into the question. All right, we got one here.
Did you end up making use of dirty schedulers for this problem at all?
So we tried using dirty schedulers to see if we could improve the NIF speed even more. But because our NIFs are really small and really, really fast, we found that the overhead of copying the binary data to and from the dirty cores was actually slower than keeping it in process. So we did try dirty NIFs, but it ended up not helping us in this case. Any other questions? One in the back there.
Yeah, so my question is just around basically using GPU. Does Erlang come with any things of basically using GPUs in order to basically use their
So the question was about leveraging GPUs and whether we'd be able to leverage GPUs. There's nothing, as far as I know, in Erlang that's built in to do that. We have looked into, there's an optimized matrix math library in C called BLAS, or OpenBLAS. And it is possible to integrate with third-party libraries like that using NIFs. We have considered using like some sort of GPU acceleration scheme and accessing that from the Erlang VM, but we're a little hesitant to, and we kind of intentionally shied away from doing anything too complicated with these NIFs because, again, any instability in the NIFs compromises your whole Erlang runtime. Any more questions? All right, that's it. Thank you all very much.